Computing has reached a scale where a single microchip can execute billions of operations every second, while AI server farms coordinate thousands of these chips to process data at speeds that were physically impossible just a decade ago. Yet underneath this massive digital infrastructure, the physical routing of all that data relies on a structural blueprint drafted in 1945, the von Neumann architecture. There is a central tension here. The design choice that originally made general-purpose software possible is now the primary constraint on how fast our hardware can run. This chart shows the exponential growth of CPU processing speeds over several decades, contrasted with the much slower improvement in memory throughput. The widening gap between these two lines identifies the primary hardware limitation of the modern era. If this 70-year-old architectural standard is currently acting as a drag on performance, we have to ask why it remains the industry standard and what alternate design will eventually replace it. To understand how computing moves past this constraint, we first have to examine the physical differences between von Neumann's design and its historical rival, the Harvard architecture. In the early 1940s, electronic calculators were fixed-function machines. They were hardwired to solve one specific type of mathematical problem and nothing else. Operating a computer like the ENIAC did not involve writing a program in the modern sense. Instead, it required manually configuring the machine's internal hardware to match the logic of a specific calculation. Reprogramming the machine meant resetting hundreds of physical switches and routing Houch cables from one functional unit to another. The logic was literally built into the machine by hand for every new task. These early machines were powered by thousands of vacuum tubes and resistors. They generated intense heat, consumed massive amounts of electricity, and occupied entire rooms just to process basic arithmetic. Because every command required a physical connection, the logical complexity of any calculation was strictly limited. Programs could only scale as far as the physical space of the room and the speed of human operators allowed. For computing to advance, the logic of a program had to be separated from the physical wiring of the machine. The turning point came in 1945 with the first draft of a report on the EDVAC, a document authored by John von Neumann and a team at the University of Pennsylvania. The report proposed the stored program concept. In this model, the instructions telling the machine what to do are stored in the exact same memory as the data being processed, treating both as identical, addressable units of information. This approach removed the need for external wiring. The machine could now read a sequence of commands directly from its internal electronic memory banks. Since instructions were now just data sitting in memory, a program could modify itself. It could automatically update its own addresses or instructions during execution, allowing for much more complex logic than physical wiring could support. While von Neumann popularized the architecture, the actual hardware built in the following years, like the EDVAC, often deviated from his specific theoretical designs to deal with the practical limits of 1940s components. This conceptual shift changed computers from physical calculators into universal logic machines, capable of running any software loaded into their memory. In 1948, the Victoria University of Manchester built the first machine to prove this theory worked, the small-scale experimental machine, or the Manchester Baby. Even to test this singular concept, engineers had to build a machine over 17 feet long, containing 550 vacuum tubes and weighing nearly a ton. Its memory was tiny by modern standards, holding just 32 words of data on a Williams-Kilburn tube, a modified cathode ray tube used as the world's first random-access digital storage device. The machine's first test was a long division algorithm run continuously to prove that code and data could interact reliably at electronic speeds without any human intervention. It took 52 minutes and 3.5 million operations to complete. This successful run confirmed that electronic stored program computing was a practical reality, establishing the hardware standard that would be followed for the next 70 years. The basic anatomy of a von Neumann machine consists of a central processing unit, containing the arithmetic logic unit and the control unit, and a single unified memory block that stores both the program and the data. These two sections are connected by a single shared signal path known as a bus. This is the defining link of the architecture. During an execution cycle, the CPU uses this shared bus to fetch an instruction from memory. Then it uses that exact same bus a second time to fetch the numerical data required for the calculation. This layout was a major advantage for early hardware designers. Funneling all traffic through a single bus reduced the number of physical pathways and components, making computers significantly cheaper to build. It also provided flexibility. Because memory wasn't strictly divided, space could be allocated entirely to instructions or entirely to data, depending on the specific requirements of the program. While the shared bus was a necessary compromise for the constraints of the 1940s, it created a fundamental mechanical limitation. It forces all computation to occur in a single file line. Modern processors can execute billions of cycles every second, but retrieving information from main memory is a significantly slower process. This speed difference exposes a mechanical flaw known as the von Neumann bottleneck. Because instructions and data share the same physical pathway, the CPU cannot fetch a new command and read or write data at the same time. One must always wait for the other. This forces the CPU into continuous idle states. It sits waiting for data to move across the bus, which caps the actual processing speed, regardless of how fast the CPU chip itself can run. In 1977, computer scientist John Backus highlighted this flaw during his Turing Award lecture, criticizing the way it limited both hardware and programming. Backus argued that we spend too much time managing the traffic of words through this narrow bottleneck, planning the movement of data rather than focusing on the actual logic of the problem. As data sets continue to grow, this shared bus creates a physical ceiling on efficiency. Every new generation of CPU must spend more of its time and energy simply moving words back and forth rather than calculating results. To solve this problem, engineers looked back to the primary alternative to the von Neumann design, the Harvard architecture. The Harvard model uses separate memory blocks and separate buses for instructions and data. This creates a major performance boost. The CPU can fetch its next instruction while simultaneously reading or writing data on the second bus, completing tasks in fewer clock cycles. However, the Harvard model is more expensive and complex to build because it doubles the necessary wiring. It is also less flexible, as memory space is strictly divided and cannot be shared if one side runs out of room. Because both designs have trade-offs, almost all modern computers actually use a complex hybrid of both systems. Main system memory still uses the von Neumann shared bus model for cost efficiency, but inside the CPU, the ultra-fast L1 cache is split, one half for instructions and one for data. We haven't actually removed the bottleneck. We have just engineered layers of high-speed cache to hide the fact that the underlying foundation hasn't changed. Today's AI and supercomputing tasks require thousands of processing cores working in parallel. This is the point where the shared memory model reaches its physical limit. Trying to maintain a single shared memory across thousands of cores creates massive delays. Constantly moving data long distances across a chip consumes too much energy and time for modern hardware to remain efficient. There is now an academic consensus that the von Neumann design is nearing the end of its usefulness. As improvements in sequential processing plateau, the focus is shifting toward designs that can better handle parallel hardware. Engineers are proposing a shift toward self-modifying dataflow graphs and neuromorphic chips. These systems remove the central memory block and the shared bus entirely. In this model, data flows directly from one unit to the next based on where it is needed. This decentralizes the workload, allowing thousands of cores to work simultaneously without waiting for a single bus to clear. The biggest obstacle to this shift is the massive cost of change. Replacing von Neumann means abandoning decades of backward compatibility and rewriting the sequential software that almost every industry relies on. The shared bus model allowed for the creation of the first general-purpose machines, but the requirements of parallel hardware are moving past its capabilities. Dismantling this 70-year-old foundation is likely the only way to truly realize the potential of distributed processing nodes.